Hey guys, we have a brand new battery here to take a look at today. This is the 12V 200Ah lithium iron phosphate model from Ampere Time with a built-in heater. That means this battery can be used in climates or locations where the temperatures are subject to drop below freezing. We'll do our usual review process here today. Overview of features, we'll do a capacity test, we'll tear it down to see how it's built inside and exactly how that built-in heater works. The battery is built in a fairly standard plastic case, as we've seen with many of these batteries. It measures 21 inches in length, 8.5 inches in height, and 8.2 inches in depth. On the front we have the brand name 12 volts. It's really 12.8 volts if you want to be technical. 200 amp hour, and it does indicate it is the self-heating model. On the top of the battery we have the standard epoxy terminal studs. They are M8 sized bolts. We also have what appears to be a serial number in the upper right hand corner. We also have a fairly strong carry handle on the left and right with a nylon strap. So taking a look at our user's manual here, we have quite a bit of information to help us get started. So like we've already said, it is a 200 amp hour battery. Recommended charge is 40 amps. And we have a continuous charge and discharge rate of 100 amps. A maximum discharge of 280 amps for up to 5 seconds, so that's going to be your surge rating. And this does have a required minimum charge of 10 amps, and that is just for that heater to function. This battery does indicate that you should mount it with the posts facing upward. Do not mount it with the posts facing downward, and ask the company if you need to mount it on its side. So we've got a very detailed explanation here on the various phases of the lithium iron phosphate charge cycle. We've got recommended settings for your charge controller. And you can connect a maximum of 4 of these batteries in series for a 48 volt system. I'm not sure exactly how that would work with the heaters, because like some of the other heated batteries we've seen, you cannot guarantee that each individual battery's heater is going to turn on and off at the same time. And we've got several pages here explaining how to connect your batteries in the various series and parallel configurations if you need. And I've completed charging this battery using my Ames 12 volt lithium iron phosphate charger, so I can go ahead and remove the charger now. So for the capacity test, I'll be using this MPP Solar 12 volt inverter, and the test load will be the space heater on low, which will put approximately a 950 watt load on the battery. And you can see we are sitting at 980 watts there, 75 amps. So our test has shut down here. Unfortunately, it was the low voltage disconnect of that inverter which powered off, and I can't program that inverter any lower than what it's already set at. So I'm going to use this little 12 volt heater here and drain the rest of this battery down until the BMS in the battery actually shuts it off, just so we have an accurate reading at our capacity test. It's just a small heating coil here with a little fan on the back. It's putting about 182 watts on the battery, still climbing a little bit. Alright, so finishing off the test here with this heater, we came in at 199.36 amp hours. Alright, that was actually fairly easy to open. It is glued the whole way around the lip here, but it's not, I don't know, it's not that silicone type glue. Alright, so with the battery open here, we've got the main negative and the main positive terminals. We see our BMS here right on the top center. We see these white leads are most likely going to the heater. Yes, they are. The battery has some foam protecting the top. It's got foam on the sides, and it appears to be set in some sort of almost looks like expanding spray foam down there, which is never fun to work with. So there we go. All right, so taking a look at our battery here, we have 8 cells. This is a 12 volt battery, and you can see they are connected in groupings of 2, then wired in series. So these 2 cells are in parallel, these 2 cells are in parallel, and then this long strip connects them into series. That means these are 100 amp hour cells each. And when you parallel them into groups of 2 like that, you now have 200 amp hours. They are laser welded nicely, and they are aluminum. We have 1, 2, 3, 4 different temperature sensors. All 4 temperature sensors are nicely adhered to the batteries. Additionally, we have our balance leads here, are terminated with a ring terminal, heat shrink, individually labeled and screwed down to tapped holes in these bus bars. So that is an absolutely perfect way of doing it. I like how these wires are all nicely routed straight up. They are held down at every point, and then the 2 sides converge here at the connector where they enter into the BMS. On the main positive terminal here, we see 2 leads coming off for our heaters. This one is labeled 12.8 volts, 35 watts. And this one is the same thing. So there are 2 separate heaters on here. There's one on each side of the battery, and you can see the heater pad here. So they've got a layer of this epoxy resin board here, And then this orange part here is the heater you can see running between this board and the battery cells the whole way to the other side. So this battery is held together with some of these nylon straps. And you can see there's actually a metal plate at each end here. And one thing I noticed that I don't really like seeing is that this strap is on here very tight, and it's so tight such that it's actually bent the metal retainer plate on the left-hand side here. And there doesn't appear to be any separator between this metal plate and the cell. And my concern is that over time there's a potential for this plate to rub into this battery. I really wish they would have put a layer of epoxy board between this metal plate and this battery, because that may have solved this problem entirely. And it doesn't look as bad on the other side, so it may just be that that plate is off center a little bit on the left. Now, one thing that's nice is that that metal plate has two carry handles on here. Does that matter because you guys won't be opening up your batteries? Probably not, but for me it's pretty cool to see that I can lift that battery up with those two carry handles there. So taking a closer look at these cells here, the QR code does start with 04Q, so I do believe these are EVE brand cells. And we see 320 watt hours, which is a 100 amp hour cell. These cells are all perfectly flat together. I don't see any bloating, anything like that. And it appears they have a layer of epoxy board between every single cell, which is perfect, so they do have some isolation from one another. So while I'm working on unbundling this BMS so we can get it off and take a closer look, I noticed there's actually a fifth sensor on the bottom here. Now this is not a temperature sensor, this is a thermal switch. And this does appear to be a VIP brand BMS, which we have actually seen in some of the other batteries we've looked at. So on the one side we have the balance leads plugged in, which I've disconnected, and we have a pair of temperature sensors. We have screw terminals here for the B- and the P-. And I haven't mentioned yet, but all of the wiring inside this battery is done with 8-gauge silicone insulated wiring. We have a pair of them, and then we have a pair of 8s for the positive as well. So on the other side of the BMS, we can see where two more temperature sensors connect. We have our negative for our heating circuit coming down to the same screw terminal here, and then we have our thermal switch here connecting to the side of that. So here's a look at the underside of the BMS here. You can see the VIP brand name. Manufacturer date is September 28th, 2021. So this BMS is a year old at this point. This connector here must be a power switch. You can see they've got the two pins soldered together there. So they could add a power switch to this if they wanted to, which would be a neat upgrade. So we've got a conductor here coming off of the P- side, and I'm guessing this is the power for the heating element. So it is coming off the P-, which means some people typically ask if the heater will drain their battery. It does not appear that this heater is running from the battery side of the circuit. It looks like it's running from the power side of the circuit. And I'm guessing these two FETs here are to turn it on and off. Alright, now we're going to test the low temperature protection and the heater of this battery. And I've sort of cheated and tested this ahead of time because it's kind of quirky, and I wanted to make sure I have a good understanding of what's actually happening here before I try explaining it. So on the right hand side here I have my bench power supply. On the left hand side here I have a DC clamp meter connected to the lead that runs from the BMS to the negative post of the battery. So the power supply will show us how much current is going into the BMS, and the clamp meter will show us how much current is going from the BMS to the battery. Now there are 4 temperature sensors on this battery, as I've noted. There are 2 on the top of the BMS where the balance leads go in, and there were 2 located on the bottom of the BMS where the heater leads go in. And it turns out that these temperature sensors have 2 separate functions. So the sensor that goes into the top of the BMS, located by the balance leads, is for the charge protection. So this sensor will tell the BMS when it should and should not charge. Now the sensor located on the bottom where the heating elements are will tell the BMS when to turn on and off the heater. So I can demonstrate that here. Going to turn up the bench power supply so it begins charging. So you see we're putting 9.8 amps into the battery, and we see that reflected on the clamp meter over here, 9.8 amps into the battery. I'm going to dip the temperature sensor for charge protection into the ice water, and you can see it shuts off pretty quickly. We have 0 amps on the power supply, and we have 0 amps in the clamp meter. So now I'll take the temperature sensor for the heater functionality and stick that in the ice water. So now what you saw there is the power supply shut off. We're now putting out 6.14 amps, and we have 0 amps in the clamp meter. So that means the 6 amps on the power supply is now powering the built-in heater. So it would seem that this bottom temperature sensor here has some input into whether or not this is charging, right? Because this should be putting out 9.8 amps, but it's only putting out 6. So now if we remove the heater sensor and warm it back up, you can see the power supply is back up to 9.8 amps, and our clamp meter is back up to 9.8 amps. So the functionality in this battery does appear to be working perfectly, and it has extra temperature sensors for extra protection. Now here's the quirky part with this BMS and this battery. As I mentioned earlier in the video, I use an MPP solar inverter for my capacity test. I typically use this Best Tech inverter here, and I don't like this inverter. This is actually a really bad inverter. And I should really make a video taking this apart and show you how it's built inside. But now the reason why I use this inverter for my capacity test, despite not liking it, is that it has a very low voltage disconnect of approximately 9 to 9.5 volts. So I can trigger the BMS low voltage disconnect in many of my tests with this inverter. And as you saw with the MPP solar inverter, that low disconnect is a bit higher, so I was not able to trigger the disconnect of the BMS. So when you connect your inverter to your battery, you'll typically use a resistor to avoid the inrush of current from the battery to charge the capacitors in the inverter from tripping the overcurrent protection of the BMS. The problem is that this inverter kept tripping the BMS of this battery, and I could not figure out what was going on. I thought the battery was bad. Now this battery sat here for about 2 weeks while I tried to figure this out, and the company kept asking me, is the video ready yet? What's the problem? And they're trying to help me out, because Ampere Time has very good customer support. But, part of the problem for me is I couldn't even explain what was going on. It seemed to me like the battery was not working. So I'm going to show you here what the problem was. You can see my indoor temperature here is 18 degrees Celsius. So I've added an additional load to the battery here. This is the 12-volt fan heater I used to finish up the capacity test. And that's going down here to the positive and negative on the power supply. So we're now putting out 9 amps from this power supply, and on the clamp meter we have 9 amps going into the battery. So when I turn my fan on here, you can see we've got 9 amps coming out of the power supply, and we've got 3 amps going into the battery. So this is consuming approximately 6 to 7 amps of power. So for the next step, I'm going to shut off the charge from this power supply. And what I would expect to happen is that this battery is going to power this fan instead of this power supply, right? So watch what happens when I stop the charging of this power supply. So the fan shuts off, the clamp meter drops to 0 amps, then the fan turns back on, and the clamp meter is showing 7.4 amps. So that is the quirky behavior I was talking about. I don't know why it's dropping the load when you stop charging. That makes no sense to me. In a standard solar application, this can happen many times throughout the day. Just think if I have a charge controller charging at 20 amps, and maybe I have an inverter with a 10 amp load, and like a cloud moves in front of the sun or something, and that charge controller cuts out for a little bit, this BMS is going to drop the load. That just seems odd to me. So I don't know if that's a defect in the BMS. It seems to be operating perfectly, so I'll assume that's based on how it's designed. Now it's not related to a thermal event because we're nowhere near where that heater should be turning on or where it should be cutting off charging. So what was happening with my inverter is I would connect the inverter with the pre-charge resistor, but then this BMS would drop the load for that split second, causing those capacitors to discharge. Then it would turn back on, which would trigger the overcurrent protection because it was trying to charge those capacitors. So when I use the MPP solar inverter, I guess the capacitors are different, so it wasn't quite tripping that protection. But yeah, that is somewhat a quirky feature in my opinion. Alright, so there you go. I will leave links to this battery in the video description if you're interested in learning more or purchasing one. If you do need a self-heated battery, this is a pretty good choice. I don't like the quirkiness of that BMS, that is a bit odd. If you don't need a self-heated battery, I would recommend maybe looking towards their original non-heated version. Ampere Time has built themselves a solid reputation for a quality battery at a low price with good support. They do have a version of this battery that does not have the built-in heater. That version sells for $649. That is a 12-volt, 200 amp hour battery. It has no heater and no low temp charge protection, so you have to keep that in mind as well. The version we have here sells for $949 with the heater, with the low temp charge protection. So it is an extra $300 for those two features. If that's something you need, I mean, that's a big price difference to me. I'd rather work on insulating my battery and keeping it somewhere where it's not going to drop below freezing. If you have any questions or comments, you can leave those as well. Hit that like button before you go, and thanks for watching.